And that is like using the Heisenberg picture of quantum mechanics. A completely equivalent picture, of course, is the Fokker-Planck equation approach. And that deals with equation of motion of wave function, density matrix. I mean, of course, in classical mechanics, you don't consider wave function, but if you want to do a quantum generalization of that kind of an approach, then you go to the density matrix or dissipative Schrödinger equation. And the analog of that is a probability function, which has also been talked about quite a bit in this set of lectures by both Dr. Sabhapandit and me a little bit, but more Sabhapandit. So that's like a phase space description, and that's like the Schrödinger picture of quantum mechanics. These two, of course, are completely equivalent description, but as far as Brownian motion is concerned, we're dealing with what you may also call continuous stochastic processes. Because after all, position and momentum variables in classical phase space go all the way from minus infinity to plus infinity and take a continuum of values. Now, there are, of course, so this is one, but there are, of course, a large class of other problems where you may have to deal with discrete stochastic processes. They don't have any underlying Langevin equation or Fokker-Planck equation. You can also call them jump diffusion processes quite generally, if you liberally use the word diffusion. And so I will talk about this system, let's say for today and tomorrow, and then come back and combine it perhaps with some cross discussions between Brownian motion picture and the jump processes. And the example that you have in mind is something that you have already seen. For instance, the coin tossing problem that Dr. Sabhapandit mentioned. Where you can have either head or tail. There's these two possibilities. And now, instead of thinking of head, you could also think of a variable which takes value +1 or -1, or you could have a case where you have a spin which can be either up or down. Okay? Now, so therefore, the problem that you have in mind is that suppose you take a large box and you have objects which are endowed with some internal degrees of freedom called spin, and each such object can have a spin either up or down, and they're sufficiently far apart that for the time being you don't have to worry about the interaction between these spins. Now the point we'd like to discuss is that even if the system is in equilibrium, T is constant, everything else is constant, pressure is constant, so the system is in thermal equilibrium, you would appreciate that if I'm in a paramagnetic regime, because I'm ignoring any interaction, that these arrows actually are not static in time, even in equilibrium, right? Even in equilibrium, these arrows, we have taken a very simple situation where I can have only two possibilities. You can, of course, have more possibilities, but let's stick to that. So these arrows are not fixed in time, even in equilibrium. They're keeping on fluctuating from up and down. Just as the velocity of a particle in a box or in this room, even if the room is in thermal equilibrium, is actually a fluctuating quantity. its mean velocity, mean value may be 0, but its fluctuations are finite, like mean squared, which goes like kt, its autocorrelation function v of 0, v of t, etc. They still exist even in equilibrium, and so do they here. So what is the meaning of equilibrium? Equilibrium means that if I do an ensemble average of these blue spins, then there will be as many blue spins up as down, and so I'll get an answer equal to 0 for the magnetization, which is the meaning of a paramagnet. Equivalently, I can choose to sit on one given spin and do an experiment where I keep watching it. What will happen? The spin stays up for some time, but then it flips down. And it keeps flipping back and forth. And the meaning of a paramagnet is that the mean time for which the spin stays up is the same as the mean time for which the spin stays down. Not true in a ferromagnet or an antiferromagnet in a sublattice, but in a paramagnet. So therefore, you can also either do an ensemble averaging over these blue spins, or actually you can look at one given spin and look at its dynamics of that spin, even in equilibrium. So that point I think one should appreciate, that even in equilibrium, one can have time-dependent quantities. So now, so physically, what may happen? So I have a paramagnet, and suppose I now apply a magnetic field in the z-axis, along the z-axis. So then, you see here it meant that up and down configurations have the same energy, but the moment I apply a magnetic field, that symmetry is broken. I have a Zeeman coupling now. The Zeeman coupling in this case is minus some Bohr magneton, etc., but let me club them all in mu, and then I have the magnetic field H, and I have the Z component of the spin. So this is your kind of Hamiltonian, the Zeeman Hamiltonian. Okay, so now up spin, where Sz is plus half, has the energy equal to minus mu h, and down spin has the energy plus mu h, and the system would like to go to the lower energy, and so earlier, before I apply the magnetic field, I had a degenerate system, but now the up state has gone, so let me call it the up state, and this is the down state. The up state has an energy equal to plus mu h, and the, this is the up now, and this is the minus. And this energy is minus mu h. So this is the up. Plus or up. Minus mu h. So what would you expect? You would expect that there will be now a reorganization of the system, and a new equilibrium will prevail when there will be more blue spins pointing up, as I have schematically in this diagram, than blue spins pointing down. And therefore, there will be a net magnetization induced now by the magnetic field. So suppose you want to describe this process, and you want to plot, I want to ask the question, what does the magnetization look like as a function of time? Magnetization, of course, is given by mu times the expectation value of Sz, and if I have total magnetization, I'll just multiply by a number capital N. So you have a situation here that you actually have a time-dependent problem, though you have applied a static field. The field is a step function as a function of time. And now, what do you expect for the magnetization? To begin with, at time t equal to 0 and backwards, because the field has been, let's say, switched on at time t equal to 0, the magnetization is actually 0, right? The magnetization is 0, and if you now wait long enough, you will see a saturation magnetization, right? So you'll see something like this. So you had equilibrium here. You also expect to have equilibrium asymptotically as time t goes to very large. But in between, you go through a non-equilibrium situation where the magnetization is actually a function of time. Now, what is the equilibrium value of the magnetization? How do you calculate it? You need some help. How do you calculate M equilibrium from your equilibrium statistical mechanics? I need some help. Hey, wake up. Yeah, very good. So M equilibrium is simply summation S, P of S, over all configurations of S, in this case only two valued, and then P of S. And so what you have is S equal to +1 or -1 in this case. So let me use white. So exponential beta mu h minus exponential minus beta mu h divided by the partition function, which is e to the beta mu h plus e to the power minus beta mu h. And that function can be written as a tanh function, right? Okay? Very easy partition function calculation that you must have done in your first year of MSc. So, starting from m equal to 0, you go to a saturation value of the magnetization. In between, you go through some process, and the characteristic time that you take to reach this equilibrium is called a relaxation time. Call that tau c or something, or tau r. And in a simple situation like the one I'm considering, I'll have only one relaxation time. We'll discover that. But you may have more complicated processes, like if you work in a glass or something where you can have multiple relaxation times. Okay? So question, how does one describe this process? Through machineries which are already introduced to you in this set of lectures. So in a sense, you can see what we are doing is the continuous time version of the coin tossing problem. So if you imagine that I keep tossing a coin, but the time between my tossing experiment can be made random. Okay? So then you'll have schematically a situation where you have a stochastic process, call it xi of t, which is now a jump process, and you start, let's say, from at time t equal to 0. So xi of t remains as +1 for some time, and then at an arbitrary time t1, it jumps to a value -1, then it stays there for some time, jumps back again, stays there for some time, jumps again, and you have something like this. At times t1, t2, t3, etc. So you have as though some discrete stochastic pulses which are really like impulses, which are like delta functions in time, which make the process jump instantaneously from values +1 to -1, from -1 to +1, etc. And what you have to do is to say, what is the mean time, mean residence time for the process to stay at +1 or -1? So that is like a coarse grain mean time, or its rate, its inverse would be a mean rate lambda. So when the distribution of these pulses is governed by what is called a Poisson distribution, that probability that such S pulses occur in time t goes like lambda t raised to the power s over s factorial exponential minus lambda t. Then such a process is called actually a telegraph process. Well, this is the way telegraphs is to be sent, and we just killed telegraphs last year, right? As you must have noticed. When we are young, starting our career in India, there was no email, there was no fax, there was no mobile telephone, there was no photocopying. All that we had to do is to do this cyclostyling. And how many copies did you use to cyclostyle for giving homework assignments in IIT Kanpur? The office helps actually disappeared because people started funding them from their projects and they would not do your work. This office stuff. There was nothing, and those cyclostyling, and we used to have telegraph at that time, right? Father serious, stop, come home, come sharp, stop. Or wife delivered a mail issue, stop. They'll always say male. If it is a female, they will not mention it in the text. Such is the bias. I can say that as a father of two girls, so anyway. So did you notice that telegraph has disappeared? There's no telegraph. The gramophone record has disappeared. CDs are also vanishing because you are now downloading music from the internet. Anyway, so this is called the telegraph process. It's a two-state jump Markov process. And so this is what we are doing, a very simple problem. I'm not going to get into these issues of persistent distribution and first waiting time distribution, which you can introduce and then get into anomalous diffusion, non-Markovian processes. We're not getting into that, where the sequence would not be Poissonian. So basically, I'm actually doing what Sanjib had already introduced, but now have added another dimension, which is the time, into the problem. So what do you do this? What is your starting point? See, as I was saying, that for Brownian motion, you use the equation of motion approach. That's very natural. But you also have a Schrodinger picture type of approach where you would start with a density operator, which is, in statistical mechanics is e to the minus beta h, and you write it as a path integral. And so that would be like your Schrodinger picture approach to Brownian motion and also quantum Brownian motion. We haven't done that. But here it makes sense to actually talk about a probability. And so you ask the question, what is the probability that your S has a given value S at time t? So S can only take two values in our problem, very simple model, +1 and -1. And so you write down this equation, which you must have all seen. It's called a rate equation, right? So what would you write? In this case, where I have a paramagnet, going from up to down is equivalent to going from down to up as far as rates are concerned. So what would you write? In any rate equation, there's a loss term and a gain term, right? So what is the loss term? That I flip the spin from the S state to the minus state with a rate lambda. So that's the loss term. But then there's a corresponding gain term where I flip back from the minus S state, right? Right? So lambda is the mean rate at which these flips occur, or lambda is actually the mean of these time durations inverses. So that's the rate constant. It's a phenomenological constant at this stage of our game, and it's a coarse-grained object because you haven't really gone into the actual distribution of these times, which has given you a lambda. Lambda has occurred through already a probability because you have said that you have an underlying Poissonian process with this probability function. So this is your simple rate equation, is also the simplest master equation that you can write down, right? Namely, let me just show you why you can write it down as a master equation, which has a structure of a Chapman-Kolmogorov equation, which is what you already talked about it, Sanjib? Chapman? No, you didn't. You're going to talk about it, okay. So for instance, you could write this P you see, suppose you use a column where you have p s equal to plus 1, let me write it little p, s equal to minus 1, and you want to do ddt of this. So in this case, you have a constant matrix W of p s equal to 1, p s equal to minus 1. So I could rewrite this equation in this particular form, where my W is a matrix, a constant matrix which has got this structure. Yeah. I don't need it. So let me actually have a half here. So you can easily verify that with this 2 by 2 matrix, I get this rate equation. And if W is a constant matrix, then I have immediately a solution which says that P of S comma T is exponential W T of P S comma 0. Okay, so this is the telegraph process, and either you can operate with rate equations or equations of motion like this, or you can actually operate with the explicit solution where you have to simply exponentiate 2 by 2 matrices. In this case, it's actually trivial. Let me just show you it, the result. Though, I'll give it as an exercise to work out through this alternate route of some of these results. So you see, you can always write this W as some lambda times the T matrix minus the unit matrix, right? As you all know, what is the unit matrix? The unit matrix has this structure. And in this case, the T matrix is such that it has got half everywhere. Can you verify that this is how you get the W? लैम्डा बाहर है. Are you happy with this? Okay, good. So what is e to the wt? Is e to the minus lambda t, e to the lambda t t, right? Now what is the property of this T matrix? If you square it, what do you get? If you square this T matrix, what do you get? Huh? T itself, right? Because you said, quarter plus quarter gives you half everywhere. So it's T itself, which means that this is also T cubed, all integer powers of T, right? So I can make an expansion of this operator is 1 plus lambda t, well, t times lambda t plus lambda square t square over factorial 2 plus dot dot dot. All the t's have collapsed into a single t, right? Right? And now the trick is to add 1 and subtract 1. So therefore, the net result is e to the minus lambda t times 1 minus t plus the rest of the series is 1 plus lambda t plus lambda square t square, etc. And I had, just 1 second. So that's e to the lambda t again. Okay? So therefore, I can push this e to the minus lambda t inside. I have 1 minus t e to the minus lambda t plus t itself. So I've exponentiated this matrix and I've brought down uh, the the only off-diagonal operator that you have in this case downstairs, so that I can easily manipulate and find and write down what the solution is, right? You could, what are other methods you could have used for exponentiating this 2 by 2 matrix? You write it in terms of Pauli spin operators and use these properties that you'll see in any quantum mechanics book like Messiah or something like that. Now, I'm not going to use this explicit solution. Just wanted to show that you can actually play with some jump processes which are of simple nature and can make explicit calculation of WT. See, all your life you are trying to find out the exponential of matrices, right? Either you're solving a quantum problem or statistical mechanics problem. Your task is to find exponential of matrices. And so often you have to do it to the computer. But there are some simple cases where you can do it exactly, which is one of these cases, the telegraph process. Okay, so now let's look at this. And let's use actually the rate equation for calculating various quantities. So for instance, suppose you want to calculate the magnetization. So the magnetization M of T has this garbage mu, and then the expectation value of S as a function of time. So what is the meaning of this now? In terms of this probability, it is summation over S times P of S comma T. This is the meaning of the average now, right? It's a weighted average over S, weighted by this probability function. So suppose I now look at the equation of motion, d dt of m of t. So that's like equal to mu summation s dp st dt. But for dp st dt, I have a rate equation or a master equation, which is minus lambda by 2 p of s comma t plus lambda by 2 p of s comma t minus s comma t. Right? Okay? Just I've substituted from the rate equation here. Incidentally, maybe many of you have seen this also, that if you have a collection of such spins which are coupled by something like Ising interaction, then the corresponding master equation like this is called the Glauber equation. If you assume that at random instants of time, the spins undergo flippings because of interaction with a bath. We are not talking about the Glauber model yet. I don't think I discussed that here. But you can just move from here to the Glauber model in one line, which is also a postulated master equation for the probability distribution. Now, of course, this equation can be simplified by using the fact that P of S comma T plus P of minus S comma T is actually 1. Conservation of probability, because I'm allowing only two values, S and minus S. So for any given S equal to either 1 or minus 1, I have this identity. So I can write P of minus S comma T as 1 minus P of S comma T. Then I get this constant will come out. I get lambda by 2 summation S times S plus or minus, and then I have same factor, so I cancel the 2. I get lambda mu summation s s p of s comma t. So what is this quantity? Is identically 0, right? Because I have 1 and minus 1. So this goes away. And this guy itself is my m of t. So I have a rate equation which says that d dt of m of t is minus lambda m of t. With a trivial solution, says that m of t is equal to m naught exponential minus lambda t. Okay? And so starting from any initial value, the magnetization, that is the average of a given spin, would decay exponentially in time on the average at a rate given by lambda, or at a relaxation time, tau r, is given by now in this model as lambda inverse. So this would be now spontaneous fluctuations, okay? And they die out exponentially if I start from an initial condition m of 0. But if m of 0 itself is 0, like I have in a paramagnetic system, then m of t will remain 0 for all times. However, I can consider time correlation functions even in equilibrium, like, so equilibrium means that m of 0 is identically 0, and so there is no question of any time evolution for the average value of the spin. But I can still consider a correlation function. So this point, you know, it keeps coming up here, and I think people should understand that simple models like this would explicitly show you that there are time fluctuations even in equilibrium. So how do I calculate, let's say, a correlation function, which let's say I denote by c of t, and that's like s of 0 at time t equal to 0, s of t. I'm not putting the superscript z for the sake of brevity of notation, because I'm only considering the z component of the spin, and it's completely classical therefore, right? So I've dropped the superscript z. So what is the rudimentary definition of this correlation function in equilibrium? In equilibrium. So the rudimentary definition of this is summation over s prime. And you are going to say, let me start off with the spin being in the state s prime. So therefore, when you calculate expectation value, remember it's a trace of a Boltzmann weight or Gibbs weight times the rest of the stuff. So this is my trace operation, the summation, and I have a p equilibrium of s prime. Then what is the meaning of this correlation function? It says that given that the spin s had the value s prime at time t equal to 0, what is the probability that I will have the value s at a time t, s at time t, and so I need to propagate. I need a propagator going from s prime to s. So that is often written as p s prime s semicolon t. So this is a conditional let me write it down. A propagator in the sense of path integral. We are not going to do that, but this actually is the same, and I think Sanjib also wrote it down. It's a conditional probability that the spin, quote unquote, takes the value s at a time t, given, it is conditional, given that it had a value s, s prime at t equal to 0. And it is this conditional probability that Abhishek Dhar will show also for a stationary Markov process obeys what is called a Chapman-Kolmogorov equation, Chapman-Kolmogorov-Smoluchowski equation. So this is your basic definition of averages, right? Just basic rudimentary definition of averages. You may not have seen it in equilibrium statistical mechanics, but they are lurking there. There are time fluctuations which you have not considered. But the moment you do an experiment, I mean, suppose here the experiment would be that you apply an oscillatory magnetic field and look at the linear response of the system. Linear meaning linear in the strength of that amplitude of the oscillatory field. And that corresponding response function is a frequency-dependent susceptibility, which in linear response theory would be related to equilibrium fluctuations of this kind. Okay? You can do that experiment, or you have a static magnetic field along the z-axis and apply a radio frequency field in the xy plane, and again look at the power absorbed, and you connect to a nuclear magnetic resonance experiment. Okay? So the physical situation that you are considering, you see, you have magnetized the system by the application of a magnetic field. So clearly your system has absorbed some energy from the laboratory applied magnetic field. So how is this how does the magnetization develop? How is it that you are able to magnetize it? It means that you are actually making the blue spins, which were in the down configurations, flip back more often into the up configuration. And as you do that, there are energy transitions going on from the up to down. And that has to be matched by corresponding transition somewhere else within the system, which is your heat bath. So your subsystem now are this, it's a conglomerate of these blue spins, and you have a heat bath. And normally these processes occur through what are called spin lattice relaxation. Through phonons. So while the spin system makes a transition from one energy level to the other, there's a corresponding phononic transition allowing the net energy to be conserved within the system in linear response. Okay? So, and it is this process that you want to describe. Again, like in the case of the Brownian particle, that guy is moving through a fluid which is in equilibrium and is sharing its energy with the fluid, and you want to look at the dynamics of that particle of interest by projecting out all the other degrees of freedom. So here you are not concerned at all, unless you really do an NMR experiment. You ask the question whether you have a Raman process or an Orbach process and things like that kind. You are not concerned with the phonons. You dump all that garbage into some phenomenological rate constants here. Okay, but behind your mind, you must be aware that you are actually dealing with a non-equilibrium process, even though you have applied a static magnetic field, and you're looking at fluctuations within the system. Okay? So let's look at that. Is there any problem of anybody in this equation? So d dt of that object is my rate equation form on the right-hand side. So again, I can massage this term. P of S prime minus ST is 1 minus P of S prime plus ST. And so I have this constant 1, and summation SS prime over SS prime will be 0 for reasons that I explained earlier here. And so, and these two terms are the same. So I have minus sign, lambda by 2. So lambda by 2 will become minus lambda. And summation. Why it is 0? Oh. What is it? So this is nothing but, so ddt of c of t is nothing but minus lambda c of t. So this is very interesting because you see that the instantaneous magnetization and the correlation function actually relax with the same kind of equation and same structure. And relaxation is given by e to the minus lambda t. So c of t is a correlation function at time t equal to 0 times e to the power minus lambda t. And at time t equal to 0 for this problem is simply s squared, which is 1. So this is actually 1. And so the spontaneous fluctuations in this model die out exponentially in time. And these are spontaneous equilibrium fluctuations which will govern the response of the system to, let's say, an oscillatory magnetic field if I want to calculate the AC susceptibility for this problem. And you might have seen this result because when you put that back in a chi formula, you'll get chi of omega. The complex susceptibility will be something like 1 over minus I omega tau r, where tau r is lambda inverse, and that shows what is called a Debye relaxation. But if you have a whole lot of tau r, like in a glassy system, you'll get into situations like non-Debye relaxations. So this is as far as equilibrium is concerned, that I have not disturbed the system at all. There's no magnetic field. I'm not considering that situation. We're only looking at spontaneous fluctuations. So please understand that I'm only describing equilibrium, however, using methods of non-equilibrium statistical mechanics, which I will have to do if you want to connect to any kind of spectroscopic experiments where either you are applying an oscillatory field or bringing in neutrons from a reactor or a synchrotron X-ray and looking at the response of the system. Those response functions are given by equilibrium fluctuations, which are usually 2-point correlations. Often you also get, not often, sometimes you get even 4-point correlation functions and things like that. Okay? So this is therefore very important for experiments. And now let us see how I can describe also non-equilibrium effects using the same formalism. Function is P1 of xi having the value xi1 at time t. Huh? And it is this guy whose equilibrium is P equilibrium, the Boltzmann weight. Okay, but you need all higher order correlations. So therefore, now you need P2, which is a joint probability that your stochastic process has xi has the value xi1 at time t1 and xi2 at the time t2, okay? And you need a hierarchy of them. Dot, 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 up to the nth term, right? The Markov process says that all joint probabilities higher than 2 can be written in terms of P1 and P2. Abhishek, you're going to do that? Okay. Right? Furthermore, I can write this joint probability. So this is what is this? This is the joint probability that xi takes the value xi1 at time t1 and xi2 at time t2. Now just imagine, I can always write this by the very definition of this probability as the probability that xi had the value xi1 at time t1 times a conditional probability that given that the xi had the value xi1 at time t1, I go to xi2 at time t2. Okay? So actually, what you have written down here is actually P2. Is P2. Is that the piece of that P2, P1 is a 1-point probability, and since you are calculating averages in equilibrium, that P1 is the equilibrium probability and is independent of time. Right? In fact, there are all kinds of projection properties also that Sanjib Sabhapandit discussed, that you can go from P3 to P2 by integrating over xi3. Or you can go from any Pn to a Pn minus 1 function by integrating out the m xi's from the problem. It's called projection properties of the probability function. Okay? Any other question? Yeah. This is one experiment that you can do. The other experiment that you can do are what are called after effect type of experiments, where magnetic after effect or elastic after effect, all kinds of things you can do. Is that you keep a magnetic field on from time immemorial, kept the field on, and you switch it off at time t equal to 0. And so here you are looking at the response of the magnetization, and here you actually look at the physically the relaxation of the. So you kept the magnetic field on for a very long time. System has come to an equilibrium where you have more spins in the up configuration than in the down, because you have now equilibrated the system with this new Zeeman energy configuration, and then you decide to switch the magnetic field off. Okay? So you will again see that you will discover a result like this. That will go down in the magnetization with a relaxation time lambda inverse. So that also you can do you can set it up very easily using the formalism that we're talking about. So now let's look at what he is asking, that what happens to m of t in this situation. And then that will allow me to introduce an important idea called detail balance. So now I am in this situation, all right, I've switched the magnetic field on, okay? And you ask the question, how does the master equation now look like, or the rate equation look, how does it look like? So unlike the previous case, okay, the lambdas are not the same, right? The rate at which the spins will flip from down to up is going to be different now from the rate at which the spins are going to flip from up to down. This is because, having put the magnetic field on, it is not equally a priori probable that the spins are either up or down. There's an energy cost, the Boltzmann energy cost, okay, or Zeeman energy in this case, right? So therefore, my rates are now different. So now therefore, I want to flip out of the state. So I have a minus lambda s going to s prime p of s comma t, s to minus s, plus lambda minus s to s, this is the gain term coming from the minus s configuration. Do you follow? There are now two rates. But you already see what is going to happen. I mean, remember, everybody, all three of us are talking about, all four of us now, are talking about steady state problems. Steady state means that the left-hand side, the time derivative vanishes. And in our case, we're actually taking steady state to be synonymous with an equilibrium state. So in equilibrium, which is the steady state here, the left-hand side is equal to 0, which means that lambda s going to minus s divided by lambda minus s going to s has this ratio equal to p equilibrium of minus s divided by p equilibrium of s. Right? I've set the left-hand side equal to 0, and I'm saying as time t progresses to infinity, this guy has reached equilibrium, so that is p equilibrium of s, and this is p equilibrium of minus s. So the rates are not arbitrary. If you want the system to go to thermal equilibrium, and see, the point is the following. Here, this is an assumption of yours, that the system does go to an equilibrium. There's enough junk in the system, enough relaxation mechanisms for which, by means of which the system does go to an equilibrium. It will not happen if you have plastic deformation, for instance, completely nonlinear effects, where you apply a stress to a deformable medium, and in the plastic regime it will flow, and you switch the stress off, it does not go back, it does not have the recovery. We are actually talking about recoverable system, and the system does go to an equilibrium. And this relationship is called detail balance. There's a whole lot of systems that are being studied at TIFR by Deepak Dhar and Mustan Barma, are driven systems where this detail balance relationship is not there. So, it's not very generic. It's true in this context of systems which are in thermal equilibrium, and you have applied not very large fields so that you don't really tamper with the equilibrium nature of that system. For driven diffusive systems and other systems or open systems, you have to do something else which is different from the detail balance condition. This means that these rates, you can easily write down what these equilibrium distributions are, because they are given by these Boltzmann factors. So P equilibrium of S, so this energy is mu h, P equilibrium minus S. So lambda S going to minus S divided by lambda minus S going to S is exponential minus 2 beta mu h S in this case. All right. So what do I have now? Now I want to do the same calculation for m of t. So now my dmt dt is equal to summation s over s prime s dps dt, and dps dt has this structure. Okay, now it makes therefore sense to say that I can write lambda s going to minus s as though it depends only on the equilibrium probability of the state that is reached afterwards, that is minus S. So that's like P equilibrium of S, and you put a factor lambda. So the ratio of these two guys, lambda S to minus S and minus lambda going to minus S to S, will be really the ratio of P equilibrium of minus S. So in this case, it's P equilibrium of minus S as given here. Okay? And you therefore have the relationship that lambda S going to minus S plus, the total rate minus S going to S is lambda P equilibrium plus S plus P equilibrium minus S, and that's just 1, so the total rate is lambda. So I therefore start writing, plugging in from the rate equation, and the rate equation is there. So I have minus lambda P equilibrium minus S times P S of t plus lambda P equilibrium plus S P S of t. Sorry, P minus S of t, right? Yeah, P minus S of t. But again, you use the conservation that P minus S of t is 1 minus P S comma t, and therefore the first term will be this term, summation over S, which goes off to 0. Yeah. No, I don't want to do that. I want to massage it here. Okay. So I also have P equilibrium of S plus P equilibrium minus S to be equal to 1. So this quantity is 1 minus P equilibrium. Yeah. Just 1 second. Give me 1 second. Yeah. Bigger size. Okay. Sure. Okay. Have you been able to follow this? No. Is it because of size or because? Huh? This one you're not following. Okay. Minus S going to S is lambda P equilibrium of plus S, so that my ratio is consistent with detail balance. Right? You agree that it's consistent with detail balance? It's not the only choice though. There are many choices in the literature. But this choice is indeed consistent with detail balance, okay? And furthermore puts a constraint on the, and for the two-state problem actually it's almost automatic, but let me not get into that discussion. Suppose I sum these two, I'll get lambda times P equilibrium of S plus P equilibrium of minus S, and that's equal to 1, right? Because probability is normalized. So that's lambda. So that's what we wrote down. Okay? So detail balance only fixes the ratio of the two rates. Detail balance does not fix the individual rates. Okay? So from there to here, there's an assumption involved. Okay, you can put in some complicated function of S there, which would still satisfy the ratio condition. But we don't want to complicate our life. Okay? Having done that, now I'm writing the equation of motion for the magnetization. And here you had this term in the rate equation, lambda S going to minus S, for which I have substituted minus lambda times P equilibrium of minus S from this relationship. Okay? Right? It's just that maybe I'm moving from one part of the board to the other, but you have to move your eyes also. Okay? And this term is lambda minus S2 plus S, for which I have substituted this. Okay? S is a variable. I can also write P. I can also write P of ddt of P of S equal to 1 comma T, and then that will be like lambda 1 going to S equal to 1 going to S equal to minus 1, P of 1 comma T, S equal to 1 comma T minus lambda S equal to minus 1 to S equal to plus 1, P of S equal to minus 1 comma T, and another equation for S equal to minus 1 T. What is your problem? You can put S equal to either plus 1 or minus 1. Correct. So why not? I'm just going from here to here. Lambda S going to minus S is not the same as lambda going from minus S to S. Yes, manifestly not. Here I have two equations then. I am lazy to write both these equations. If you want me to write it down and want me to work harder, then you have another equation.
Yes, but the thing is, if you condense them both into one equation,
then it's perfect.
no, then it's not right, because the lambda that you write there is misleading, because it's different in one equation, different in the other equation.
I don't know what you're talking about. Say it honestly. It's valid for both S equal to plus 1 or S equal to minus 1. I'm just writing in a compact way. In fact, when you have more spin states, are you going to write for the n equation separately? Oh, bhar jayega your sheet. I mean, you know that when you would write down the equation for, maybe when you are writing Glauber equation or going to the computer and modeling it every day, not worrying about the notation. What do you write there? You write TDT of P of a configuration of S1, S2, S3 all the way up to Sn comma T, and you write down this rate summation over J, loss term and gain term. Just one equation that has n differential equations, and I'm only writing 2 in terms of 1. Okay. This equation is just valid for a general S. In this case, S only takes values plus 1 and minus 1. Okay. I have written P equilibrium of minus S as 1 minus P equilibrium of S by using the normalization condition. So therefore, I have this is I have minus lambda summation S P equilibrium of S. Sorry, let me do it carefully. Just that I think this heat, I'm getting tired. Okay, let's take the lambda out. I have summation S plus P equilibrium of S, P of minus S comma T. So this will give you lambda times summation S, P S comma T. And have I missed a negative sign? I have a negative sign. This is negative, and so this is a negative sign. Right, Abhishek? Yeah. So this is a negative sign. And the rest is minus lambda summation S, P equilibrium of S, P S comma T plus P minus S comma T, and that's equal to 1 as well. So now we are almost through. So this quantity is actually m of t itself. And minus I have, sorry? Second number should come plus. But yes, because of an overall minus sign. Thanks. Second term? Yeah, lambda is an overall factor, no? So there's a overall lambda. Yes, thanks. So what is S P equilibrium of S? Is exponential for S equal to plus 1 minus divided by the two cost functions. So this is equal to minus tan hyperbolic half beta h m, beta h mu. So therefore, I have minus lambda m of t plus lambda tan hyperbolic half beta h mu. So that's very nice, because that's exactly what describes this problem, because you have dm dt is equal to this, and so as time t in the steady state, m will flip to the other side, and you get this tan hyperbolic function, which is what you expect in equilibrium. Okay? So this is your m equilibrium. So the point that I wanted to make is that basically you're using the same kind of master equation the rate equation because you have a very simple situation here. More complicated cases are when you have a many body spin configuration, let us say. But within the same set of equations, you can describe either equilibrium or non-equilibrium cases within the same formalism. Okay? Now, I have 10 minutes. So let me tell you what I'm going to do tomorrow and perhaps day after. You can get away by doing phenomenological classical theory because you really did not go into the micro details of transitions from one state to the other. But indeed, behind the scene, you are considering transitions of spins from one eigenstate to another. These eigenstates are the states +1 and -1. So you actually have a quantum problem at hand. It's just that we didn't want to worry about the detailed quantum mechanics of this. But now suppose you want to do that. How would you translate this problem into the quantum domain? And of course, you have already talked about dissipation because the moment you write rate equations, you have tacitly incorporated dissipation into the system. These are dissipation parameters, lambda. So how do you make a quantum jump? So start writing a Hamiltonian. Which in this case has a minus mu times h, and you had an sz term, right? For a single spin. Okay? But you considered all of that junk in the system, though you did not explicitly, because you had all this other stuff which is causing the spins to flip. So now if I ask you the question, what on earth would cause Sz to flip from one eigenstate to another? What on earth would cause a spin to flip? Or what is the operator that would make a transition from an eigenstate of Sz from one state to the other? Let me actually take sigma z. Yeah, either I can work with say S or sigma. All right. So what is it? Sorry. Yeah, very good, excellent. So if I have a sigma x, now as you know that sigma z, these are these Pauli matrices. This representation, and in the representation in which sigma z is diagonal, sigma x is an operator which has got this structure, and then you have sigma y to complete the set, right? So they have this SU2 algebra, and as he pointed out, that sigma x is purely off diagonal, because if I take the diagonal components at 0, but it's purely off diagonal, that's equal to 1. So sigma x would indeed cause sigma z to flip, but we need something else to twiddle this, just as I was saying that this transition is accompanied by a phononic transition in another system. So you need something like a phonon operator to couple to sigma x, okay? And so you assume the linear coupling that occurred in the Swansig-Ford et al. Model, where if you recall that when we had a term like Qj minus Cj and over some Mj omega j Q squared, and then you have half Mj omega j squared, you discovered a linear coupling which was Cj QJQ. Okay? Now you adopt now the same philosophy, and actually in the context of spin lattice relaxation problems, this is called a linear phonon coupling model, where you see these are QJs of the jth oscillator, and the QJs are like in the second quantized notation Bj plus Bj dagger plus some prefactor. So you can use these bosonic operators. And Q, however, was a coordinate of this Brownian particle earlier, which of course wanders around over all space. So Q belongs to an infinite dimensional Hilbert space. But now your Q is truncated into a two-dimensional Hilbert space of a two-state system. So that's actually like a sigma variable. Okay? And so the model that you use is GQ BQ plus BQ dagger. That's like this coupling term. And then you have this still the harmonic oscillator energy for the jth oscillators. And then you get summation Q H bar omega Q BQ dagger BQ. Okay. So this would be a model to describe exactly the kind of physical situation we have in mind, where you interpret these B's as phonon operators, and while sigma x causes transition between the eigenstates of sigma z from either up to down or from down to up, simultaneously BQ and BQ dagger in the occupation number space of the phonon system will make transitions of the phonons from one occupation number to another, right? Because BQ and BQ dagger are also completely off diagonal in the representation in which the number operator is diagonal. And this is your number operator. So now we see you have a generic model for describing dissipative quantum systems, because you have this model as a model where you have a subsystem Hamiltonian, which is this. You have a bath. This is going to be a bath in the same sense as in the Swansig model. And then you have an interaction term which couples this system, because after all, this is actually a coupling between the sigma system, the subsystem, with the external bath system. So you have a generic problem of your Hamiltonian being splittable into a subsystem, an interaction term, and a bath. And like we did in the context of quantum diffusion, quantum Brownian motion, we'll have to average or integrate out the bath degrees of freedom, namely the B degrees of freedom, and discover or retrieve equations of motion for the sigma system. Okay, I'll come to that. Okay? So this is a direct jump to this problem, and if you want to study spin lattice relaxation problems, you may have more complicated coupling, but even through this linear coupling, you can describe what are called acoustic phonons, optic phonons, etc., depending on the spectral function that you use. We use the ohmic dissipation model. That will break down when you are really talking about phonon systems. So here it is an example where your bath is a bosonic bath, and they can, however, have different kinds of spectral functions. Now, the point that he made is that, you see, you can actually juggle with this Hamiltonian, and you can make a rotation in the spin space about the y-axis. You see, here is x, z, y. Now, if you rotate about the y-axis, then z becomes x and x becomes minus z by an angle pi by 2. So if you apply a rotation operator on this Hamiltonian by pi by 2 about y, then your z becomes x. So this Hamiltonian goes over into, well, z becomes minus x, I think. So because I am doing a rotation, I'll use a rotation correspondingly, pi by 2 or minus pi by 2. So I'll get a mu h sigma x plus sigma z times the same operator. This rotation does not do anything to the phonon system. Now, historically, this is a model that was talked about by Leggett and others in the context of tunneling problem. So suppose I have a symmetric double well where your particle of interest, which could be a proton or it could be a positive muon or something like that, most of the time are at the bottom of the two wells, which you map into the two eigenstates of the sigma z operator. So this is like your +1 state, and this is like your -1 state. And suppose you create a wave packet at time t equal to 0 around this well. So the particle is localized there, and you let the system go. What will happen is that this guy is going to go back and forth like a quantum clock, and that process is called tunneling. And so tunneling can be described by this term, because sigma x has off-diagonal terms between +1 and -1. So sigma x will make these transitions possible, just as they were making transitions here. So that's like a quantum clock. It's a very coherent motion. So this term will give you coherent motion. But this term is obfuscating the z variable because it is coupled to another field which is being jiggled by the harmonic oscillator term. Because in the interaction picture, you can imagine that BQ and BQ dagger are going to acquire time dependencies. And so they are like fluctuations. And those fluctuations means that they're making the z, sigma z fluctuate. So these are blurred, and so that will introduce the coherence effect. And this model, as our friend pointed out, is called the spin boson model, which is basically the same model as this one. Now, then there are other generalizations. For instance, actually in realistics, okay. So this symmetric double well has some very, very interesting and important properties. And let me just mention this, because it is contact with the Kondo problem. See, in a Kondo problem, you have a magnetic impurity inside a metal, okay? Now, this magnetic impurity, if it is a spin half impurity, then that is like your spin sigma. And this magnetic impurity couples to its own electron cloud around, okay? And then, of course, there's electron-electron interactions. But it turns out that as long as you are happy with simply looking at electron-hole excitations of the Fermi surface, the fermionic bath has a Tomonaga-Schwinger form of being represented by the bosonic bath. And so the Kondo problem is a version of this problem where if you use this ohmic dissipation, which is what is appropriate, then there's a very interesting situation that, as I said, there is coherence phenomenon of a clock going up and back and forth. But now you think of jacking up the strength of this noise, that is strength of the coupling, which comes to the spectral function. Remember, the spectral function for the ohmic model has this omega squared over some behavior. So you put a coupling constant, and usually that's called capital K in deference to Kondo. And it turns out that for a particular value of K, which actually is 1 in that case, K 1 or 2, that's called the Toulouse limit, in which the particle doesn't just tunnel at all. It gets localized in this well. So there's a dynamical symmetry breaking transition in this model. That is because if you write down the path integrals, you have an underlying Ising model here. And that's the work by Munich guys. You know him very well. He worked with Leibowitz or Munich. Spohn, Herbert Spohn, who showed that, Herbert Spohn showed that you can write it down as an Ising model. Anyway, so there is a dynamical phase transition that if you increase the coupling constant, which will be there in the spectral function beyond a certain point, then the particle does not tunnel at all. It gets localized. So there's a localization transition also in this model, in the symmetric problem. But very often, you don't have a symmetric Hamiltonian, like hydrogen in niobium. You have, because they have long-range elastic interactions, you have an asymmetric double well. So if you have asymmetry, that can be easily incorporated by adding another term, which you call H times sigma z, plus mu H sigma x, plus the same coupling. So that is like an asymmetric double well. And that problem has been extensively studied in experiments also, because that's the problem of hydrogen moving in niobium, and lots of neutron scattering data on that. Well, there are other many examples, like, as you know, that there's this old paper due to Anderson, Halperin, and Verma, where they argued that the glassy systems at very low temperature has two-level excitations. So if you want to describe quantum effects, especially for metallic glasses, let's say at very low temperature, use these models. So there are many, many such examples. And then, of course, this qubit problem, a qubit problem. One of the basic models of quantum optics also is like this, when you see Rabi oscillations in a two-level atom, and you couple that to a bunch of photons, and the photons also have this kind of a bosonic structure. So you can have this block equations for the sigma x average and sigma z average, which are also very generic to quantum two-level systems in quantum optics. So this model is actually quite rich. And the classical version of that is simply the two-state jump process or the telegraph process. But in quantum mechanics, you have to have the dynamics of BQ and BQ dagger incorporated to describe such problems. So tomorrow onwards, I will talk about some properties of these quantum models, which you can then compare with what you have hopefully learned today in the classical version. I'll stop here. I was supposed to stop now, or I was supposed to stop now? Okay.